PhD student at the University of Edinburgh, where he is working on updating the algorithms for super real-time fire modeling. He obtained his degree in mechanical engineering in Chile, and he also holds a master's degree in mechanical engineering from the same university. His master's thesis is about the radiation modeling of copper concentrate combustion, and he has done consultancy with DICTUC in South Africa? SA? It's an incorporated. Okay. Where I come from, it's South Australia. So, and Codelco as well. From 2005 to 2006, he worked for the LAN airline. So, thank you.
Good afternoon.
Click on the.
Okay, thank you. The work I'm going to be talking about was made in the context of FireGrid, which is an integrated emergency response system specialized in fire, where one of the main topics is obviously fire modeling. We want to give the firemen or the fire brigades an idea of what to do in the case of a fire. Well, fire modeling has obviously gained a special interest after the events of 9/11 because people wanted to know what happened. They wanted to know why the buildings collapsed. And it gained special interest after that. However, the reconstruction of fire scenarios is very difficult because generally we don't know what happened. We don't have any measurements. Generally, the CCTV camera recordings or maybe the time when the smoke detectors went off are the only measurements or the only data we have of to know what happened inside the fire scenario. Another point that complicates furthermore the reproduction of fire scenarios are the unknown room layout, because they can change, like desks and chairs can be moved around, so you don't know how the fuel loads looks like in the event of a fire. An example of all this was that the WTC simulation is the first one that were made by Kevin McGrattan, I think. Were based entirely on visual recordings. They saw the fireball and they tried to reproduce the size of the fireball, but they didn't have any idea of how it looked like inside and what really happened. Okay, I'm going to run through this because most of you probably know what this is all about. And there are basically three types of models. Identity models based on correlations, very simple, but can give a good idea of what is going on. Zone models, well, yeah, you all know how it works. And the most complicated, most complex way of doing this is using CFD field models. Field modeling has been displacing zone modeling because we can do it now. We have more computational power, and we don't need to use just zone models. And many people, you have much nicer output, and so people tend to prefer that over zone models. The problem of CFD fire modeling, however, is that it's a huge challenge for scientists still. There's no complete CFD code for fire available yet, and it's going to be a long time until we have one. Another problem is that CFD validation is based today on simple enclosure fires, where the little pool fire is put in one place of the room, and then temperatures are compared or smoke movement is compared. But there's no comparison between a fire of a real fire and the modulation of a realistic fire scenario. A year ago, in July 2006, the University of Edinburgh conducted real-scale fire tests in Glasgow, where they burned, as we saw before in Ian's paper, a flat, well, two flat actually. The key difference between the Dalmarnock tests and previously large-scale tests is that we had very dense measurements, which were the scale of comparable to typical grid size. So we had 270 thermocouples, video cameras, heat flux gauges, and velocity gauges at the entrance of the vents. So we had a good knowledge of what was going on during the fire. And here you can see the compartment. There's a sofa in the middle of the room with a little waste paper basket. This was ignited. The fire would spread to the sofa, and this started burning. The idea was to make the fire spread to the bookcases here and to simulate a corner fire. There are two vents, two doors to the kitchen, to the hallway, and all these white lines are thermocouple racks. There's 20 of them and 12 thermocouples on each rack. This is how it looked before. This is how it looked before after the fire. There's not much left, as you see. Here's a little table of the events that took place in the fire. At the most important one, at 300 seconds more or less, the flashover occurred or started occurring. So after that, the whole main compartment was burning. So why do we want to do it? What's the motivation of doing a posteriori simulation of the Dalmarnock fires? As we saw before, there was a round-robin blind study, and it showed that blind predictions of fires are of realistic fires are very complicated and really not possible with the state-of-the-art fire modeling tools. You can see some results from the round-robin. From round-robin, there, as you see, there a large scattering in the results, and there's no real consistency between temperatures and heat release rate. So what we wanted to know, up to what degree we can reproduce fire scenarios if we have full access to all kind of measured data. Furthermore, we wanted to evaluate which variables have the most important impact on the fire, on the course of the fire, and which one we have to give to our simulations in order to be assimilated into a super real time simulation as we want to do in FireGrid, or as we want to do in FireGrid. Regarding our simulations, we had the ignition source, as in the tests, was the sofa. So we had the access to a sofa lab test done by the University of Edinburgh. We had a little problem to match this to the recordings from what happened really at Edinburgh at the Dalmarnock test. So we used other tests as the NIST test to come up with a proper ignition source. And once we had the ignition source, we had to think about fire spread. There are basically three possible approaches. Two of them prescribed, one predicted. We could use a t-square fire growth. We could use measure the heat release rate of all the items in the room and then add them up and put them in as an input into into the FPS or CFD code. And the third way and most complicated way, but at the same time the best way, would be to predict the heat release rate. To simulate the flame spread based on the material properties. The T-square fire, we didn't want to use that because we had many different items in the room. We wanted to maintain the physics of the room. So we wanted the sofa to burn and the bookshelves and everything. So we didn't want to take all this out, and because we couldn't relate the parameters of the T-square fire to those items. So we then decided to use an impose, to add up all the individual heat release rates and put them as an input to